this is north. And the stream is over here. So the map that I'm showing here is a little bit rotated, and it's a bit idealized. What I'm going to say is that I've got a straight stream, and that these two wells are oriented. The line between these two wells is parallel to the stream and perpendicular here, and that's pretty close to what we have in the field. And then if I were to do a cross section going around like that, perpendicular to the stream, it would look something like this. This is just a conceptual cross section. You can see I just drew it by hand, but it gives you a little bit idea of what the subsurface is like. We've got saprolite, and then there's a transition zone here, and then fractured rock underneath it. And the upper 30 feet or so of the rock has significant fractures, fractured rock aquifer. The saprolite is about 50 feet thick, and the water table is up in the saprolite. You can see it up here, and the water table is just continuous with the water here in the stream. The depth to water is about 25 feet of Theis zone, and here are the well spacings and the 140 feet. Okay, so that's what it looks like roughly. This is our conceptual model. Okay, so we did a test. This is done a few years ago, and we monitored 6 wells, and the drawdown as a function of time plotted on a semi-log axis is shown here. There are all 6 of these wells. And then the pumping well, so there are 7 well, let's see. Yeah, the pumping well is not shown on here. These are all monitoring wells. So there are a few more wells here than I showed you on the map. What I'm going to do is just focus on 2 of the wells here. But you can see that all of these wells are behaving really pretty similarly. And then we've got some other ones here that are different. In general, what we see is that the drawdown goes kind of curves up, and then we've got a semi-log straight line portion in here, and then the slope flattens out, and they're all doing more or less the same thing, although with a bit different magnitudes. So these are all wells that are completed in the rock. This well here, it's called LAS1. This is in the saprolite, and you can see that we've got some drawdown in the saprolite, and then we kind of lose the drawdown here in the saprolite. So it's not really quite clear what happens with the saprolite. Reservoir case, but also it will allow us to include a constant head boundary. The Neuman solution, this is for an unconfined aquifer, and we can also evaluate the infinite case and the case with a boundary. And the Coolean case solution, this is for an unconfined aquifer over a confined aquifer. So I selected this one because the saprolite is unconfined, and we might think of the underlying rock as confined. And again, this one would have infinitely acting and constant head boundaries. Now, one thing to point out is the Aqtesolv allows us to include a constant head boundary in several of these solutions. And the way that it does this is using a technique called superposition. So if we look at a well here, and if this is the initial head, and we do a pumping test, and we generate head that looks like that. So we've got some drawdown, and right now, let's say we're in an aquifer that looks like this of infinite extent. And we want to say that, well, what I would like to do is assume that there's a boundary right here. And let's say that it's a constant head boundary. And if I look at it in map view, it's a straight boundary that goes in to infinite extent in the in and out of the plane that we're looking at here. So the way to do this is if I use a solution that is for the infinite case, I can put another well over here. Let's call that, this is an imaginary well. And if we put an imaginary well over there at a distance L from the boundary. So this is the boundary. And L is the same distance that my actual well is from the boundary. And if this is pumping, if I make this well an injection well, then the heads will look like this. So it's going to be the same as the heads here, except they'll be positive instead of negative. And what happens is, as I continue pumping on this well, if the solution then looks like this, the actual solution for the infinite case, if I have an image well, it's going to look like this, the heads for the image well. And if I add these two together, here this is 0, and so the actual well says that there's drawdown at the boundary of that much, and the image well says that there's buildup of that much. And when I add them together, they're equal but opposite in sign. And so when I add these two solutions together, they give me 0 at this boundary. So this is a convenient approach, because what it means is we can take solutions like the Theis solution, the Neuman solution, the Cooley-K solution, that are written for the infinitely acting reservoir, and we can use this superposition technique to introduce a constant head boundary. We can also have a no-flow boundary, and we can have multiple boundaries. So Aqtesolv is really quite convenient. It gives you this fairly convenient methodology for including boundaries. But we need to keep in mind that these are really idealized boundaries. So it's a constant head boundary. So it would be like we had a stream that cut all the way through the aquifer and held the head constant. Okay, so what I want to do is take a look at these individual cases and look at how the kind of information that we can get by fitting these solutions to the data that we have from this pumping test. So we'll start with the Cooper-Jacob analysis, and what I'm showing here on the left side is a page from this software Aqtesolv, and it shows a conceptual model, this sketch here, along with some of the equations. And what this is showing is that we've got a confined aquifer here, and we've got these properties, transmissivity and storativity, and this is a confining unit, and this is the piezometric surface up here in the confining unit. And then we've got a governing equation and these terms here that are used in the theoretical analysis. So what I'm showing over on the right side are the data here from these two wells, the LAR3 and LAR2, and it's plotted on semi-log. And you can see the data here are the same data that we showed on the previous slides, or 2 slides ago, I guess. And so for the Cooper-Jacob analysis, what I'm doing is fitting this line here to the straight line portion, right in here. This is what I say is applicable to the Cooper-Jacob. And you can see that it fits pretty well. But in order to get the fit, I have to say, well, I know the Cooper-Jacob is not applicable at early times, so I'm just going to ignore this. And the Cooper-Jacob is not including a boundary. So I think that this is not this infinitely acting reservoir. So I'm just going to ignore that. Okay, and if I do that, then I can fit it, and I can get T and S, and there they are. Now, we could use an automated curve fitting approach for this. Aqtesolv has that built in. And if we do it, this is what we get. Okay, and this line fits the data set the best. So if we didn't know what we were doing, and we just said, okay, I'm going to take the best fit line, this is what we would get. But it would not be really a correct interpretation, because we're assuming that the Cooper and Jacob is really only applicable to a certain part of the data set, this semilog straight line part. So fitting it fitting it to the whole data set is just not going to be appropriate. And that's a really important thing to keep in mind as you use software like this to interpret pumping tests, that you need to understand what the assumptions are for the various analyses and what part of your data are applicable to those assumptions. Okay, so the next one that we'll take a look at is the Theis solution. It's got the infinitely acting case and the boundary, and here are the same kind of information from Aqtesolv that we saw previously. The configuration is pretty similar, except we also have the ability to have an anisotropic aquifer where the hydraulic conductivity in the z direction is different than the hydraulic conductivity, in the z direction is different than the hydraulic conductivity in the r direction. And that's pretty common in layered sediments, for example. So this is the fit of the Theis solution to the infinitely acting radial flow case. And you can see this semilog straight line portion we can fit pretty well. And with the Theis solution now we can fit this early time data pretty well. Remember, we couldn't get this with the Jacob analysis because it didn't do early time, but the Theis does, and it works pretty well. Okay, so then I said, well, we've got this part here that the Theis solution really can't explain. The Theis solution is just going to come up and continue on in this semilog straight portion. But if we introduce a boundary, then the boundary will cause the slope to change. So I put a boundary in Aqtesolv at it turns out it's minus 140 feet. And I'll show you the setup here in a second. But if I do that, then you can see that causes the slope to flatten out. But it causes it to flatten out at a higher, well, it's happening a bit too late, and it's not really flattening out at a low enough head to be consistent with the data. So the behavior is right, but the timing and the magnitude is not really right. Now, remember, the pressure, the drawdown, is propagating outward. And what we see is that right about at that point, you can see that we start to get a break in slope. So this is when the drawdown reaches the boundary. But we can see in the data that it reaches it right about here. Okay, so this 140 feet, the actual distance to the boundary, seems like it just causes the boundary effect to occur a bit later than it actually occurs. So what I did was say, well, okay, what if the boundary really was closer? What if it was at minus 45 feet? And I adjusted this distance a bit to get it to work out right. And if it's at minus 45 feet, then look, that it fits really quite nicely. It fits this semilog straight line part. It doesn't get this part quite right. The change in slope is a little more gradual right in here than the data. But here where the slope is starting to flatten out, it hits it pretty well. And one thing that's kind of interesting too is see how LAR2 and LAR3, they're the same radial distance from the well, but the heads here or the drawdowns are different. And so when we have an analysis that doesn't include that boundary, that we get the same drawdown at these two wells predicted. There's not really any difference between them. But because we have a boundary, the configuration is like this. Here's the boundary, and this is LAR2, and this is LAR3. So what's happening is the boundary is causing the heads in LAR3 to be lower, or the drawdown, less drawdown than it is in LAR2. And that's because LAR3 is closer to the boundary than LAR2. Okay, so that makes sense. And so we're getting some insight into maybe an explanation for why the drawdown in these two wells are different, even though they're the same radial distance. But the problem is that the boundary, in order for that to work, the boundary would have to be a bit closer than it actually is for this conceptual model. Okay, so there's some insights. We can explain the data, but we have to have this assumption about the boundary that is a little different than what we see. Okay, so now we want to introduce the Neuman analysis. This is for an unconfined aquifer. And one of the differences here is that we introduce this parameter, the specific yield, in addition to the storativity. So remember, the storativity gives you the elastic portion of the change in, or the release from storage, and the specific yield is a pore drainage effect. So here's the data for the infinitely acting case, and I adjusted the parameters so I got the best fit that I could. And in this case, I'm specifying that the anisotropy, the KZ-KR ratio, is equal to 1. We could change that, and I show an example down here where it's not equal to 1. But I thought, well, I didn't really want to have that be a factor. I just wanted to fit for these three and see if I could explain the data. And so what we see is that up through this part, the solution looks pretty similar to the previous solution for the Theis case, for just a confined case. But then we have it flattening out like this, and this is where we start to get, well, this is where it starts, and then this flattening of the slope is the release of water from the unconfined aquifer. And we said, well, what we expected conceptually is that we would get a good bit of release of water when the water table first started to drop, and that would cause the drawdown to flatten out. But as time goes on, the drop and the drawdown would diminish. And well, as time goes on, we're going to have to get additional drawdown to remove water from storage, because we've gotten the water out. Well, we just have to, we have to get additional drawdown to remove water from storage. And so what happens then for this case is that we have a flattening of the slope, but it's just a temporary flattening. And with time, the slope curves back up. Now, if you look at the data, it flattens out and it's not really curving back up. So for the for the Neuman, it says that it should start curving back up, in this time frame. But we don't really see that. Now, that's okay. Maybe there's something going on that delays it, and maybe really the data would kind of go like that. So it still has the same behavior as the Neuman, but there's just something that would delay this upturn. But this is going to be an important effect, because remember what we saw in the previous analysis is that this flattening out, we could explain that with a boundary, with the Theis solution. But with a boundary, it's going to flatten out and it's not going to curve back up. But with the release of water from the unconfined aquifer, it does curve back up. Okay, so it seems like we have some aspects that are pretty consistent with what we see. And let's then introduce the boundary. So in this case down here, I put a boundary at 140 feet. And you can see that there's really not much difference. And so what I conclude from that is that, well, the boundary at 140 feet, it's just really too far away to have an effect for this unconfined case. Now, what's going to happen is the pressure wave will propagate more slowly through the unconfined aquifer than through the confined aquifer. So it's going to take even longer to get over to the boundary for the unconfined case than it does for the confined case. So that kind of makes sense. Um, so we don't really see with this Neuman solution, we don't see evidence for the boundary. But if we bring the boundary in closer to 30 feet, then what happens is we can see these. We can see in this case here, this uptick in the drawdown gets flattened out. Okay, so that that is really looking a lot more like what we were expecting the data to be, except this boundary is closer than what we really see. So we're getting some indications that we could explain the data from using this unconfined release from storage, at least this break and slope. But this end part of the data, at least for the Neuman analysis, it curves up more quickly than what we see in the data. Okay, so now we've got these two approaches, or really two conceptual models for explaining this break and slope. We could do it with a boundary. The boundary needs to be a bit closer than what we see, or we could do it with release from storage and unconfined. That explains the break and slope, but then it's just this late time that is not explained. So that's some progress. One thing I should point out too is this specific yield. So that specific yield of 0.5, and that's the maximum specific yield that I allowed. And so specific yield is going to be, it can't be any greater than the porosity. And saprolite can have pretty high porosity. I've measured porosity in saprolite up to 0.6. So it might be possible to have specific yield that's that high. This is higher than you usually would think. You would probably usually think something more like 0.2 to 0.3. So this might be a bit on the high end. And what happened was when I did the fit, I for this fit actually I used the automatic fitting capabilities in Aqtesolv, and when I did that, I constrained the specific yield to be a maximum of 0.5, and the automatic fitting just selected that maximum value as the best fit. Also, down here, so there's the anisotropy ratio, and you can see that's quite small. That means that the vertical hydraulic conductivity is much smaller than the horizontal hydraulic conductivity. And that kind of makes sense because our conceptual model for this aquifer is that it's this fractured rock, and there are several fractures that we can see in the borehole that are sub-horizontal, and that if you average that out, it would give a horizontal hydraulic conductivity that's greater than the vertical. But I should also point out that this effect here, the effect of this anisotropy, it's a fairly small effect. So it helps fit the data a bit better, but it's a fairly small effect. So this is not really a number that's determined with a lot of confidence. There's a good bit of uncertainty there. Okay, then the last model that I tried was this Cooley and Case model, and this is a good bit more complicated. We have an aquifer here that's characterized by TNS, a confined aquifer, and then we've got an aquitard here that has a water table in it, and we're not really allowing horizontal flow in this aquitard, but we can release water from storage due to changing the hydraulic head in the aquitard. And so we've got a hydraulic conductivity, a storativity, a specific yield, thickness, and that L is the thickness of the capillary fringe. So I went through the conceptual model and came up with some of these dimensions for example, the thickness here, and hold on just a minute, I gotta turn on this pen. For the thickness, there's the capillary fringe, and I need to have an estimate for that's the storativity of the confining unit of the saprolite and the specific yield, and I need to have their ratio. And the reason for that is because the Cooley case analysis requires that I specify several new parameters. Some of the groupings that it uses are shown here. These are groupings that it's going to solve for. And then it's going to require that we specify, I don't see, it's probably got cut off, but it's going to require that we specify this, the ratio of those storages, as well as the ratio of B prime and L, that term right there. Okay, so I just went ahead and calculated those up based on my conceptual model. For just the basic analysis, there's the curve, and you can see it fits the data pretty well. It looks pretty similar to the Neuman analysis. We get a break in slope, and the drawdown flattens out, but doesn't flatten out completely, still has a positive slope, and then it curves up here at the end. If I include a boundary here at 140 feet, then I get that curve, and if you compare these two, I really don't see much difference. You know, if you look right there at that cluster of points, and there you see the curve coming through it at almost exactly the same place, and then let's take a look at those points. You know, it's essentially unchanged. So what we can get from that is that over this time period, during the course of the test, this boundary at 140 feet, it just doesn't really make any difference because it's too far away. But if I move the boundary in closer, say I move it to 20 feet, in the analysis, then here's what I get. I can get a really good fit to both data sets. I have the curve split, and here both curves are the same, but these curves to split up because now the boundary is quite close, and the positions of the wells are different relative to the boundary, right? The boundary is here. The stream, it would be like a stream right here, pumping well, and one monitoring well is there, and one monitoring well is there. The monitoring well with the greater drawdown, LAR2, is further away. Okay, so that's interesting. We get a really good fit to the data, but it requires that this boundary is at 20 feet, which is much closer than the boundary actually is. So one aspect of the Cooley case analysis that's a little bit different than some of the ones that we saw earlier is that one of the consequences of it being a little more geometrically complex, you know, it includes both the aquifer and this confining unit, and we get these additional terms. And so what Cooley case did is group the terms together into these quantities B and beta. And these are groupings that they solve for. And in the results, then if you take a look at the results here, I don't know, hopefully you can see well enough that right there, that's L over B prime. And this one is S prime over SY. And those are the two values that we specified. So we didn't solve for those. Those we specified. And then that term that says beta over R, and that says 1 over B, and we have some values. And then here are the values T and S. Okay, so what do we do with that? Well, this is b, and we can take this value 1 over b, which is 0.048, and I can write out what 1 over b equals. And then I can take a look here and say, well, I know t, I was given that, that's right there. And b prime plus L, I said earlier that from my conceptual model, I know that that's 52.5 feet. So that means I can solve this for K prime. That's the hydraulic conductivity of the saprolite. So I did that here, and just drew out some of the terms. And if I fill in the values here, then go through and multiply that out and check the units. Those cancel, and I'm going to get feet per minute. And I do that out, and I get that for the hydraulic conductivity of the saprolite. So that's pretty nice. The other tests that we did, the other analysis, they weren't really giving us information about the saprolite, and this one does. This gives us this hydraulic conductivity value. I can get the hydraulic conductivity of the aquifer because I'm given the transmissivity up here, and I know the thickness, so I can take the definition of transmissivity and solve for the hydraulic conductivity. And I get that it's this value, a little bit less than the hydraulic conductivity of the saprolite. And then what I did was just work through here. I usually think of values in terms of, I use SI units a lot, so I usually think of it in terms of meters per second. So I just went and converted it and got the hydraulic conductivity of the rock into is 5 times 10 to the minus 6 meters per second, and that's fairly reasonable value for relative to other analyses that I've done for the fractured rock in the Piedmont. Okay, so that's working with B. Now this beta over R term here, that's beta over R is equal to that. And here I just wrote it out. So we just solved for K prime, and B prime we are getting from the conceptual model, 50 feet. We already solved for T and S. So this is what we don't know. So we can take beta over R and solve for S prime. Okay, so I go and do that. Just multiply both sides by 4 and then square it, and I get that. And then I can solve for this, and I go through and I get that. Okay, so this is the storativity, and this is a pretty high value for storativity if it's an elastic storage, and it's low for specific yield. So yeah, that's kind of an intermediate value. But I also, on the previous page, I specified, you can see up here, it's getting kind of crossed out, but I said that one of my assumptions was that S over SY is 0.01. So I've just solved for S prime, that's the storativity of the confining unit, and I can solve now for the specific yield. So I did that here, and if you go through that, you get that the specific yield is 1.3. Well, we know that the specific yield cannot be greater than the porosity, and the porosity, the largest porosity I've measured for saprolite is 0.6. So this is impossible. You could not have specific yield this high. So that's something that I think we need to just look at a little bit more. When I did this analysis, I decided that I would assume this ratio of these two storage terms up here to be 0.1. But maybe that's incorrect. Maybe I need to go and revisit that, and then I could go and revise the analysis. So if I were to make that a little bit smaller or a little bit larger, then I would need to solve the analysis again and go through these calculations and see if I could get this to be a little bit more reasonable. this kind of thing, this kind of issue here, is one of the things that you often see where you have a complicated analysis. Well, where you have an analysis with a lot of different parameters and a relatively sparse data set. Um, that there are just a lot of parameters that you can adjust to get the curve to fit. And so as a result of that, there's going to be uncertainty because the solution, the matching of the data can be non-unique. And that means you could match the data equally well with a variety of different combinations of parameters. So I suspect that something like that could be going on here. So we'd want to look at that in a little more detail. Okay, so that's the Coolean case analysis, and I went and summarized the parameters for these four different methods, the t and s values that all of them gave, and then some of these analysis I included a boundary, and what I'm showing here is the distance to the boundary for the solutions that would fit the data the best. And then some of the analyses gave me specific yield. I converted the transmissivity to the hydraulic conductivity of the aquifer. And then these are the storativity and the hydraulic conductivity of the confining unit. So what you can see by comparing these is that these first two analyses that assume the aquifer is confined, they give a transmissivity of 0.8, 0.08, 0.09, something like that, and a storativity of 0.006. And then if I assume that it's unconfined, I decrease the transmissivity by about a factor of 3, and I decrease the storativity by a little bit, but I also then have this specific yield. So one of the consequences of including the specific yield is that we reduce the transmissivity by, by a factor of 3 or so. And then if I go to Coolean case, I get really a similar transmissivity, and in this case, a reduction in the storativity, and then apparently this very large, anomalously large specific yield. So I have a question mark there because, I mean, maybe we should just have an X because we know that that's not really going to be a value that makes sense. So we need to revise analysis a bit to see if we can get something more in the range. But what it's kind of hinting at is that the specific yield is quite large. We could make some adjustments and I think get it down and maybe get it down to that range. And that maybe that brings this up a little bit. Or yeah, maybe I'm not sure about that. But it would adjust it a little bit. So I guess, well, and I guess if we look over here, the hydraulic conductivities, they vary by a factor of 3. That's pretty small range really. And the hydraulic conductivity of the saprolite bit higher than the hydraulic conductivity of the rock. These values here are quite reasonable. These values here are quite reasonable for the storativity, and these values here I think are okay. But remember, for these values of 0.5, that's what we said was the upper limit. So one of the things we can say is that really both of these analyses that are including the water table, they fit the data pretty well, but they're not able to really constrain the specific yield value very well because I mean this is just not right, and then this one is just the maximum value that we specified. It could be that if we just if we didn't specify this, maybe it goes up to this unreasonable value too. So we can't get really too comfortable that we've really nailed down the specific yield with this. but we can say that these analyses that include specific yield can explain the data really quite well, that break in the slope. They do a pretty good job of that. We also took a look at the effects of having a boundary on fitting the data, and we could fit the data really pretty well with the Theis solution with a boundary at about 45 feet, and that did not include any kind of specific yield. And when we had a boundary, really one feature of all of these is that when we had a boundary, it separated out the curves and separated them out in a correct way. So it seems like that's suggesting that there's some influence of the boundary, but we really don't expect that this flattening out of the slope is a result of the boundary, because with all of our analyses, in order to get that, the boundary was too close um, to, to be realistic, and a realistic boundary really didn't have any effect. So what I think all this is telling us is that when when we have data that look like this in our test, that this is giving a fairly consistent value for transmissivity and distortivity, within a factor of 3, say. And the break and slope, I think this break and slope is because of the specific yield, um, and the pores are draining, and that's causing the slope to flatten. Now we saw that these solutions are indicating that the drawdown will increase, but we haven't seen that in the data. So there may be some other things at play that are extending out the time when the drawdown will increase in our field case. So that'd be something that we'd want to watch out for. It could be that the the yield from the unconfined aquifer is responsible for this initial break in slope, and then it's not coming up because it starts to interact with the boundary out here at later times. Maybe something like that is an explanation. Um, yeah, that's possible. We'd have to look at that in a little more detail. But in any case, I think that this has given us some pretty good insights into what's happening at our site. And it also gives us some additional things to think about and to look at perhaps with further testing. We might go and continue working with some of the other data. We've got some data in the saprolite that could be useful, although we saw that earlier and it didn't really give a clear indication of a response in the saprolite. We have some other measurements in the rock, so we could continue on and see how those data can be fit with these kinds of analysis. But this is an approach that I think is useful, where you take the conceptual model, and based on that, you develop some analyses that will be relevant to that conceptual model, and you evaluate it. And you almost always will start with one of these analyses, um, and then proceed from there.